Okay, so we're at week 5. And one thing I wanted to check with you all about, and I'll send an announcement about this if I can figure out a way to do a poll through the announcement, maybe I'll do that. But we have this modeling growth 1 next time, and then we're going to have introduction to Bayesian methods, and then I'm going to talk about multi-level logistic regression, and that's going to be the main topic actually, but then we're going to sort of continue our talk with Bayes. And then after that, I had planned for this modeling growth 2, and specifically there, I was thinking about talking about piecewise models, and then some other more advanced ways of handling nonlinearity. So next week, we'll talk about things like polynomials and things to handle nonlinearity. But piecewise models themselves can handle nonlinearity in some ways because you have this like break. But I was also thinking about covering like splines. And the nonlinearity stuff is not like necessarily specific to growth models, but that's where I use it most. So I was thinking about covering that. But the other option is, instead of doing that, because we already have one topic on growth modeling and a lot of the examples have been through growth models, the other thing I was considering is extending from here and talking about things like models for handling count data and things like that. So like Poisson distributions and negative binomial and whatever. So if you have a preference for one of those, I'll send out an announcement, like I said, and I'll try to get your feedback. But that's like kind of where I'm at in terms of prepping the slides. I'm prepping these right now. Then from there, I'll start on these ones, and I'm just not sure which would be more useful for you. So I will probably be asking for some feedback there, unless people have thoughts on that right now. Anybody wants to share? All right. Okay, so today, the main topic for today is variance-covariance matrices. And I will give you another, like 20 minutes at the end of class for homework 2. We will go over that, and then you'll have a chance to ask questions and get started on it and see if you have any problems or anything. Okay, but we're actually going to start out by reviewing modeling notation that we introduced last time. And specifically, what I'm going to do is I'm going to show you some models. I'm going to have you load some data, and then I'm going to show you some models in equation form, and then ask for you to fit that model with code. And then we'll go through like 5 or 6 examples like that. Okay. And then we'll talk about variance-covariance matrices. Specifically, we'll talk about what the default is with LME4, and then some alternatives and how you would compare different models with those different variance-covariance structures to see what sort of is fitting the data best. Okay, so the learning objectives, hopefully you'll gain a deeper understanding of the residual structure in different multi-level models. The one set of models that we'll talk about uses GLS, and I'm not sure, I think you would probably still refer to them as multi-level models, but the way that they estimate the residual structure is pretty different. So it's not like the analog is not direct there, but they still handle the residual variance covariance matrix in very similar ways. And then understand that there are methods for changing sort of the defaults that you get with a multi-level model and why that might be preferable. The main thing there is mostly just overfitting. So the default tends to be very, it estimates a lot of things. And sometimes you want to maybe simplify that structure to get a better fit to the data where you're not overfitting and fitting to errors in the data. And specifically, you might run into convergence issues if you're trying to estimate like 7 random effects or whatever. Okay, and then hopefully you should be able to, by the end, implement some of those alternative methods in LME. I'm only going to really cover a few of these, but there are tons of them. All right, so we'll just talk about sort of the ones I think of as kind of like the main structures, and we'll have all the code to do that. And then you can dive deeper on your own later if you want to. Okay, so notation, we're going to review some of the Gelman-Inhill notation. So let's start by using the sleep study data from LME4. Okay, so just load LME4, And then you should be able to say head sleep study, and you'll get a data frame that looks like this. So I'll give you a minute there. Okay, hopefully you have that done. And now we're going to do this. Okay, so here's a model where we have reaction time, and it's modeled by these things, and then you've got subject here. Okay, so I'll give you 2 minutes. Go ahead and see if you can try to fit a model that is equivalent to that. Okay, hopefully you were able to get through. What I would do here is look at this as we know reaction is the outcome, right? So that's helpful. But then when we're looking here, the first thing you should probably notice is there's no other predictors in the model, right? There's nothing else in here. And we're saying that reaction is distributed normal with some alpha j, right? And alpha j itself is assumed generated from a random normal distribution, okay, with some mean and then some variance. So what we're saying here basically is that we have separate means for every subject, okay? So that's another way of saying we have an intercept that is randomly varying for every student, or every subject, rather, okay? So it should look like this. Any questions on that? Okay, now let's try this one. This is just a little bit more complicated. 1 minute for this one. Okay, so with this one, this is basically the same as the last one, right? The only difference is now we have this term. And so we have our alpha ji, and that is randomly varying, right? We have alpha j is randomly varying across subjects. But days is not. We just have one of them, just one B1 days, okay? So that should look like that, okay? We have days as a fixed effect. You could have 1 plus days, right, if you wanted to be a little more explicit. Days as a fixed effect plus 1, as in your intercept, is randomly varying across subjects. Okay? Questions on that? Okay, now we'll go a little bit more complicated. So 1 more minute, extend the model so it looks like this. Okay, so in this case, now we have beta 1 j, right? So now not only do we have alpha j randomly varying across subjects, but we have beta 1 j randomly varying across subjects. Okay, so we have alpha and beta are assumed generated from now bivariate multinormal or bivariate normal distribution with means for each fixed effect, and then this variance-covariance matrix. So this part is really kind of what we're going to be focusing on today. Okay, so that looks like this. And again, you could have 1 plus days and 1 plus days here, and that's going to be the same thing. Okay? Any questions on that? Okay. So now there's this data sim3 level. It should be in the repo, but Brock is telling me that it's not. So let me go look.
There's a link on your slides. I found it real quick by linking from the bottom of your slide to that.
Yeah, it should be there. Yeah, it's there, Brock. This is it right here.
Okay, maybe my GitKraken's a little backed up.
Yeah, so that's, it should be up there, and it also should be on Canvas. So let me just make sure. If we go to Files, and then Data, let's see, where is it? Yeah, there it is, right there, sim3 level.csv. So it is on Canvas, and it should be through the GitHub repo. And then there's a link right here. So either way, you should be able to grab this data. Okay, so I'm going to give you 1 minute to get the data and get it read in.
Is there any reason you always use like read_CSV instead of just import when you're using the here package?
Yeah, so read_CSV is from the readr package. import is from Rio. So there's just different ways of doing it. Rio is nice because it'll read in anything. Most of the time I'm reading CSV, so I just use read_CSV. Import is actually going to be probably faster though, because it uses data.table, which is like the fastest thing for data manipulations in R. So import's great. I don't know. When you load the tidyverse, readr is already loaded, so then I don't have to load another package. That's basically it.
Okay.
Okay, so we have a bit of a problem with these data. Okay, it's actually not really a problem, but it's a problem for Equasiomatic to produce the equations. So I decided that we would talk about it here a little bit, and then we'll fix it. Okay, so if we look at this, if you say sim3, which is the object that I read this thing in as, right? And I say count classroom and school, you can see that the classroom goes 1, 1, 1 for schools 1, 2, 3, right? So these are actually 3 different classrooms, and they are nested in these schools, okay? And so we could, as I talked about before, use the LME4 syntax to handle this directly to say that the classrooms are nested in schools. But I prefer to just have explicit IDs. This nesting of IDs just makes me nervous because it's like, it just seems to me like it would be possible to have this classroom and think it's this one because they have the same ID, right? So it is the combination of these two things that gives you the unique classroom. So again, it's not really that much of a problem, but Equasiomatic doesn't like it. I maybe could fix it, but I haven't. So instead, I decided to make a class ID. Okay, so here's something I'm calling class_ID, where I'm just pasting class and whatever the classroom is, and then a colon, and then school. So this says class 1, school 1, right? And then when we get to the class 2 school, it would say class 2 school 1, right? But then we would also have another one that's class 1 school 2. So this is a now unique class ID that is going to be, right, each individual classroom is uniquely identified by that ID. Does that make sense? Okay. So now we're going to fit the most complicated model we've fit so far. So here it is. I'm going to just let you look at it and try it first, and then we'll talk through it, okay? So try to fit this model. 2 minutes. Okay. So here we go, right? So we have math as our outcome. That's pretty clear. And then when we're looking at this part, right, we're saying math is assumed generated from a normal distribution that has this mean structure, right? And alpha is our intercept, and notice that we have a J and a K here, right? And then if we look down, we can see we have class ID and school, okay? So our intercept is going to be randomly varying across class ID and school, okay? For active time, we have beta 1J. So active time, we have beta 1J here. J is indexing class IDs, right? So active time is randomly varying across class IDs, but not across schools, okay? And so then we end up with something like this, right? And again, we could have 1 plus, but we have math, active time for class ID, and then plus 1 pipe school. And again, the reason that we can do these random effects separately like this is because we have those unique IDs. If we did not have those unique IDs for class ID and we wanted to specifically say that they were nested, then we would have to do school : class ID. Okay. Questions on that?
I've got a question, Daniel.
Mm-hmm.
So we have active time as a fixed effect and as a random effect by class ID there. Is that,
Yes.
am I interpreting that correctly?
So you're basically saying whatever the effect of class or of active time is on math scores, right? That effect is going to randomly vary between classrooms within schools, right? But you're saying you're going to assume that it's fixed across schools, but within a school, it's going to randomly vary between classrooms.
Got it. Thank you.
Mm-hmm. Other questions?
If we do put the colon to say that the classes are nested in the school, that is still equivalent even with this this type of syntax, right?
Yes. Yep.
Okay. Just
It should be exactly equivalent. If we look back at the slides, I think it was from last time, there's an example where I have the model specified both ways, and you can see it's exactly the same. Okay, now a little bit more complicated. Try this one. Okay, so when we're looking at this one, we see that we now have alpha j k, right? Just like we had before, so the intercept is randomly varying at both levels. But for active time, we have beta 1 j k, so it's now randomly varying at both levels also. Okay. In addition, we now have this class size variable here. Okay. When we're reading these, right, we always say normally distributed, and then this is the mean part of that, and this is the variance part of it. Okay. So class size is basically predicting the class intercept mean. Okay, the class intercept. And so in LME4, we're just going to add it in like this. Okay, so we have active time that's randomly varying across class ID and school, but then we also have class size that we're just adding there. Okay, and the reason that we can do that is because the variable itself only varies by classroom. Okay, so if you look at the actual data itself, it will only vary by classroom. And this is again where I've mentioned before, like the multi-level structure that we think about is very helpful, but it's also important to keep in mind that multi-levelness is just a heuristic, right? It's not real. There's nothing really multi-level model about it. Okay, it's just a regression model like any other, except you're estimating these randomly varying parts. Okay, and so if you have a variable that only changes by classroom, then that's going to predict classroom level variance. Does that make sense? So it's not like we have to add that variable at level 2. We just need to have the variable itself only be randomly varying at level 2. Or not randomly varying, but you know what I mean. Like if it's a class size variable, then obviously it's going to be constant within a classroom. Okay. All right, last one. This one's pretty complicated, but see if you can do it. Okay, so here we go. This part's all the same as last time, but now here we have class size as a predictor of the intercept and as a predictor of the effect on active time. All right, so we're saying basically whatever active time, whatever that impact that has on math scores, that relation is going to depend on class size. So maybe in smaller classrooms, it's a bigger effect, and in bigger classrooms, it's a smaller effect. Okay, that's what this is specifying right here. Okay, notice we also have here at level 2, at the classroom level, we have class size gamma alpha 1k, right? So class size is also varying at the school level. Okay, so at the school level, we have alpha k, beta 1k, and gamma 1k. Okay, gamma 1k being this one. And then those are just specified with the means, and then we have the variances of each of those as well as the covariances. Okay, so in code, that's going to look like this. And we could put this a little more explicitly, but this asterisk is going to specify the interaction between active time and class size. Okay, that interaction is what this is right here. Okay, so another way to think about this is, and I actually tend to like to write these out a little more explicitly, is you could say active time, which would be this one, plus class size, which would be this one, plus active time colon class size, and that would be this one. Okay, does that make sense? And then in terms of the random effect structure, we have active time varying across class ID, and then at the school level, we have active time and class size varying across schools. Okay. Any questions on that? All right. What did you think about this exercise? Yeah,
I
go
have
ahead.
a request, I guess, but this is putting more work on you, but you made this package that does it quickly. So if you could let me know if this is really hard. Could you make like a not for points, just like quiz we could do of this that has more examples? Because I feel mixed feelings on these depending on how complicated the model is and would love more practice.
Yeah, so that was actually exactly where I was going to go. I was asking, I was going to ask, did you feel like this was useful? Which it sounds like yes. And then the second question is, would you like to repeat this again next week? Go through this same sort of thing. Okay.
Yeah, very helpful.
All right. I will plan to put together another thing like this. We'll take the first half hour or so of class and do it again. Okay. All right. Okay, moving on today for the residual structures. So the data we're going to use is from Willett, 1988. So this is from this book right here, Singer and Willett. This is a super good book if you're doing longitudinal modeling. It's a little bit old at this point, but it's still really, really good. I don't know if they have any code or anything. They use SAS, so they don't use R, but it just has lots of good examples and lots of good things. So if you're doing longitudinal modeling, I have that as one of the course recommended books, but it's not required. But if you're doing a lot of longitudinal modeling, I would encourage you to check that out. Okay, so this is data from that book. From the data, the book isn't from 1988, but the data are. This is from a study from 1988. 35 people completed a cognitive inventory on opposites naming, okay? And at the first time point, participants also completed a general cognitive measure, okay? So you should have this data either through Canvas or through the repo. It's called Willett 1988. So go ahead and read in the data and it should look like this, okay? Give you a minute or so. Okay, so standard OLS, right? Ordinary least squares regression. So we have 4 observations per participant in this data set. And if we fit a standard OLS model, it would look like this. So instead of LME-R from LME4, we just use LM. We say opposites naming. It's predicted by time, and the data are Willett. Okay, so I sort of went over some of this at the end of last class, but I'm just kind of reviewing it here. So I called this bad. When we call summary bad, there's our stuff. Okay, the reason this is bad is because we have this residual structure that looks like this, right? So we have opposites naming is predicted by some intercept, and then some relation between the intercept and time. But then this E, the error, is this assumed well, I'm missing the N there for normal. But from a normal distribution with a mean of 0 and some unknown variance, which we estimate from the data. Okay, so the individual level residuals end up looking like this, right? So this is expanding out the notation that I just had on the previous slide to make it look more like a multivariate normal distribution. So each of these is like a row of the data set, right? And so we have one variance that we're estimating that is constant across all rows, okay? And all the off diagonals are 0. So you've probably seen the IID assumption before. That stands for independent and identically distributed, okay? So that's what this is. When we're looking at this diagonal, identically distributed means we have one variance, right? They're identical in their distribution. That's the assumption. And then they're independent because all of these off diagonals are 0. So one row of the data set has a residual, and that residual is independent of all other residuals, okay? And we know that that is not the case in this data set because each person has 4 rows, right? And so we are violating this assumption because unless you're making the assumption that if I were to take a test at one point and then I take it again a week later and those 2 scores are going to have absolute nothing to do with each other, then you're violating this assumption, okay? And so what we need to do is instead of estimating just this single residual, we need to estimate additional components, okay? So then we end up with this block diagonal structure instead. And this is like really big and it looks scary, but it's really not that scary. It's basically the same thing I just had, but now we're sort of breaking it out so that each person has their own residual structure, right? So instead of just saying E1 here and E2 for the first and second row, we're saying E11, 12, 13, 14. So the first, second, third, and fourth rows for the first participant, right? And then the first, second, third, and fourth rows for the second participant. And so what we see is we have these variances at each time point, and we have all these covariances as well. Okay, whatever this structure is here, that part is still assumed identical across participants. Okay, and so all of this is review anyway, but same variances for each block. The off diagonals from those blocks are still 0, but those correlations within a block are estimated now. Okay, so this, because we have that same block structure for all participants, that's what's known as the homogeneity of variance assumption. Okay, so basically within a block, within a person, the residual structure can be heteroscedastic and dependent, right? So the relations between time points for an individual can depend on each other. But the entire error structure is repeated identically across people. Okay, so it can be heteroscedastic and dependent within a grouping factor, but not across. Okay, so that ends up giving us this block diagonal structure that looks like this. So because of the homogeneity of variance assumption, right, because this thing is going to be the same for every person, it looks like this, right? This is often referred to as the composite residual. We can sort of summarize what the whole thing looks like this, right? So it's mean of 0, but with this residual structure where sigma r is equal to this. Okay, so now we're going to start actually fitting some models to the data, and then we're going to dig into this residual structure a bit. Okay, so let's start by trying to fit a parallel slopes model with the Willett data. Okay, I should have had the equation here, but I don't, but that's okay. Try to do that. Okay, so parallel slopes, that means, right, every subject is going to have their own slope, but those slopes are going to be assumed parallel. So they're all having their own starting point, different starting points for each participant, but then the rate of growth is going to be the same for all participants. So that looks like this, right? Opposite naming, predicted by time, and then +1, so our intercept is randomly varying across IDs, okay, with the Willett data. So what does the residual variance covariance look like? I asked you through an announcement to install this sundry package previously, so hopefully you have that installed. Is there anybody that does not have that installed? Let me ask that first. Okay, so you're going to load sundry, and then you're going to use this function pull residual vcov. Okay, and then from there you just feed it the model, whatever model you fit, and it will pull the residual variance covariance matrix from that model. Okay, so I'm calling this thing W0 RVCV, residual variance covariance. All right. If you call image on that thing, it will then give you an image of what that residual variance covariance structure looks like. So you can see this is like basically the rows of the data set, right? And you can see this block diagonal structure that we have here. Okay. If we want to pull the first couple of rows and columns, we can do that like this. Okay, so I use brackets to get into the thing, and then I'm pulling the first 8 rows, the first to the 8th row, and then the first to the 8th column. Okay, and I used the first 8 to show you that whatever the variance covariance, residual variance covariance matrix looks like for this participant, it looks exactly the same for this participant. Okay. So when we look at this residual variance covariance matrix, you can see these off diagonals are all the same, right? That's all the same number just repeated a bunch of times. And here on the diagonals, we also have the same number repeated all the way across, okay? This is because we've only estimated one additional variance component. So rather than just having sigma, which would be just 1, we're estimating that plus residual variance in the intercept. And so we have two variance components, which we can put together like this, okay? So let's look at this a little bit closer. I'm not sure why I have that there. This is the model. So we would say, right, just in terms of interpretation really quick, that subjects started with an average of 164 points, and they progressed at 26, about 27 points per wave, or however time is coded, I don't remember. And this initial starting point varied between participants with a standard deviation of 30. Okay, so again, when we're looking at this, we see we have this variance component, which is 30. We also have this variance component, which is about 20. That's sigma, right? That's the residual variance. So this is the variance between participants in the intercept, and this is the leftover residual variance. Okay. So we can use this function called varchor to actually pull out the variance covariance numbers from a model. Okay. And if you wrap that in as.data.frame, you'll get a fairly nice looking data frame that has both the variance covariance number, but also the standard deviation. Okay, so this is nice because back here we have these reported in standard deviation units, which we could just square those to get variances, but this puts it in a data frame. Okay, so we have the group is ID. For the intercept, variance is 904. For the residual, the variance is 375. Okay, so let's go back here for a second. 904, right? And then 1280. Do you notice anything there? Right, so, the diagonals are just this part, right? It's this intercept variance, or the off diagonals, sorry. The diagonals is basically the total variance. So it's this plus this. Okay, so 1280 and 904, if we add these two numbers together, we'll get 1280. Okay, and then this one's 904. So this is code to just sum that if you want to. So including more complexity, what I'd like you to do is try to fit this model and then use sundry to pull the residual variance covariance matrix. Okay, I'm not sure if we'll need 4 minutes, but I'll give you a few minutes anyway. Okay, give me a thumbs up emoji if you're done, or give me something else if you need more time still. Okay, good. That looks like most everybody. Okay, so here's how I would do it, right? First, I'm going to fit the model, which is up as the outcome with time, but now I'm just going to have time randomly varying across the IDs, so the intercept and the slope. Okay, when I pull the residual variance covariance matrix, here I'm just showing the first 4 because now we know that it's the same for all students, right? But we get something that looks like this. Okay, and so what we can see is that now the variance at each time point is different, and the covariances are different. Okay, so we're estimating quite a more complicated residual variance covariance matrix here when we're estimating multiple variance components. So this is generally what is referred to as an unstructured variance covariance matrix. It's not fully unstructured, and I'll show you why here in just a second. And near the end, I'll show you how to estimate a fully unstructured variance covariance matrix. There is some sort of disagreement about the way that you would communicate this model. In Singer and Willett, I think they call this model the standard multi-level model, right? To distinguish it from like the fully unstructured variance covariance matrix. But at least in the circles I run in, people would generally refer to this as an unstructured variance covariance matrix. Okay, so while each block is still going to be the same for each participant, we have different variances at each time point, and we have different different covariances. Okay, so what are these numbers? I'm not expecting that you're going to be memorizing this equation or anything, or even using this equation, but I did want to show you what is happening here, okay? Because what we're estimating is still just our residual variance, intercept variance, slope variance, and now the correlation between intercept and slope variance, okay? So that is back here, right? If we look at this, we can see all of those components. Intercept variance here, slope variance here, correlation between intercept and slope variance here, and then residual variance here. Okay. So that residual variance covariance matrix is given by this. Okay, so we have our sigma plus our intercept variance plus this is our covariance between them, and we're going 2 times that covariance times wave, right? So 1, 2, 3, 4, and then plus our slope variance times our wave squared. Okay, so that would go 1, 2, or 1, 4, 9, 16. Okay. So we can do this by hand. Again, this is like background information. This is not something that's super important. It's just for further depth of understanding of what's going on here. Okay. So I'm grabbing the variances, and then what I'm doing here is I'm just pulling the pieces of that out. So this is the intercept variance, this is the slope variance, this is the covariance, and then this is our residual variance. Okay. And so what we can do is we can say, okay, give me the diagonal of our residual variance covariance matrix, and this is just just the diagonal. Okay, so it's this part. I'm getting this number, this number, this number, and this number. Okay, and then I'm going to try to use this equation to try to recreate those. Okay, so this is what it looks like. For the first one, it's the residual variance plus the intercept variance. Okay, for the second one, it's residual plus intercept plus 2 times the covariance plus slope. Why is the covariance and the slope not included in this one? Anybody know? Because they're getting multiplied by 0. Okay, because our wave goes 0, 1, 2, 3. So I said that wrong when I was squaring them just a second ago. But so if at our first time point, when we're using this equation, this is multiplied by 0, this is multiplied by 0. So we're just saying the residual variance plus the intercept variance. Okay. And then we just continue on with that equation. Notice we have squared here for the second and third time point, and we can replicate those numbers. Okay. So what was the point of doing that? I've kind of already mentioned that. I don't really care if you can do that, but the main point is that residual variance covariance matrix, right, for the block diagonal, the composite residual, is just a transformation of these variances and covariances that you're estimating. Okay, so we can do the same thing with the off diagonals. This is a little bit more complicated equation, but it's still not that bad. Here I'm doing it for just a couple of them, and you can see I get the same results here as, so I'm doing it for the first diagonal, the first row of diagonals below the variances.
Daniel, can I ask a question that is probably just very simplistic, but I think I'm curious about, like, you know, when and how and why we'd use this. Like, are you doing this every time is this when you're saying just like data exploration? Like, I guess I sometimes get lost about like when and why you'd use this, when you'd actually report this, would you?
Yeah.
Yeah.
So if I'm doing a standard multi-level model, I would not report this for sure. The reason I'm showing you this at this point is mostly just background information. In a little bit, we're going to get to models where we're changing this residual variance covariance matrix, and that's because we'll be estimating different ones that simplify the model. Okay, so you can so this is the default, but you don't have to use this. You could use alternative residual variance covariance matrices, and often there's simplifications of this, and that will occasionally lead to better fitting models.
Okay.
And the other thing is, it's not just better fitting, but often when you're trying to estimate all of this stuff, your model fails, right? It won't converge. And so one way around that is to simplify this residual variance covariance matrix.
Okay, so this is all like just related again to model fitting, like understanding your data and how to best fit models that aren't over or under fit, I guess.
Yes, exactly. So, and at this point, this is really just background information that I'm hoping will help you better understand when we go to changing these things, how they're different from what the default is. Good question. Okay, so let's go ahead and take a 5-minute break now at this point. And then when we come back, we will talk about other residual variance covariance structures. Okay, so let's come back at 10:33. Okay, so positing other structures. Okay, so there are a whole bunch of different alternative variance covariance structures that you could fit. And so we'll talk about a couple here, some of the most common. And then from there, hopefully, you'll be fitting some of these as well. And then if you want to go deeper from there, you can. But I think these ones that I've sort of brought out are, I think, the most useful. So Singer and Willett, Chapter 7, that's sort of the place to go for this kind of stuff. There's a link here too to all the code to fit these models. So I referenced that as I was building these slides for a couple of different pieces in particular. Okay, so the structures will fit. Unstructured, which is the default for LME4, so we've already seen this, right? Will also fit a variance components only model, so no off diagonals at all, okay? Will fit an autoregressive model, and then heterogeneous autoregressive model, and then this Toplet's model. I don't even know that if that's how you say it, but it's something like that. So this is just a sampling. Again, there are other structures. But outside of the unstructured and the variance components only model, you are going to have to use an LME. Okay, and you should all have that because it's one of the recommended packages. So when you install R, it's usually installed for you already. But if not, just run install.packages in an LME. You should be good. Oh, yes. Also, if you want, as in a couple weeks, we'll talk about Bayesian estimation. So estimating multi-level models using Bayes instead of maximum likelihood. And using the BRMS package, which is what we'll use, you can fit some of these as well. Okay, so variance components only. So generally, in a model like the Singer and Willett data, right, we would estimate intercept variance and slope variance. So everybody has their own starting point and everybody progresses at a different rate. Okay, we saw earlier how these combine for the residual variance covariance matrix, but alternatively, we could just estimate separate variances at every time point. Okay, so then instead of estimating, well, one residual variance plus intercept variance plus slope variance plus the correlation between them, we would just estimate a variance for time point 1, a variance for time point 2, a variance for time point 3, and a variance for time point 4, and those would all be different. Okay, so it would look like this. I am not suggesting that this is the best model, particularly for like growth models. This is almost never really going to be the best model, and we will see that later on. But for other types of models, it might make sense to actually estimate a separate variance for every school or whatever, right? And not estimate any of the correlations. Or another example is, like, let's say you have a random intercept and a random slope for like active time like we had before. You could estimate each of those variances, but not estimate the covariance between them. Okay, that's a pretty common example. So if we wanted to do this for the data that has time points, right, we would use what's called one-hot encoding. And this is exactly the same as dummy coding, except you use all the levels. Okay, so that might seem strange because it's like, well, how can it estimate all of them? But what we'll do is we'll actually drop the intercept and then we'll estimate each of these. Okay, and so this is true of fixed effects as well. If you want to estimate all the levels of a categorical variable, you could actually drop the intercept, and then you don't have to use you don't have to have a reference group. You just estimate the means for every category. Okay, so this is how I would do it if I just had 4 waves of data like this, where I would just say if time is equal to 0, then 1, otherwise 0. Okay, so here's t0, time here is equal to 0, so this is equal to 1, and then for all these other time points, it's equal to 0. Okay, and then when time is equal to 1, 1, otherwise 0, when time is equal to 2, 1, otherwise 0, etc. And we get dummy codes basically, but we have all of the categories, so that's called one-hot encoding. Okay, that makes sense? Okay, so yeah, this is quick aside. We can also, instead of doing that, we could also use model.matrix. Okay, it's a internal function that does the dummy coding for you normally. So you could say model.matrix and then you give it a formula. In this case, I would just say 0, so say drop the intercept, and then plus factor time, so make time a factor, and then R will see that as categorical variable with the Willett data, and then it would create data like this for you. Okay, so this is a data frame. You just then have to bind that data frame to your existing data frame. So this is an aside. It's not the most important thing. This way will always work. The only reason that this might be helpful is if you have a factory where you have a bunch of different levels of it, or you have time that's coded in a much more complicated way, but then you're probably going to run into estimation issues also. So it's just an alternative. Okay, then we're going to fit the model. And there's sort of 2 things here that I want you to notice, right? We have same outcome, same predictor for time. We have intercept as well. But then when we specify our random effects, we're going to say 0. So don't let the intercept vary randomly across IDs. Instead, have T0 randomly vary across IDs, and T1, and T2, and T3. Okay? And then for the part that separates what's randomly varying from the units, ID, instead of having a single pipe there, we're going to have 2. Okay, so you're going to go bar, bar there, right? And that double bar like that is going to say estimate all of these variances, but don't estimate the covariances. And again, this doesn't have to be for time point data. It could be something like we have, a bunch of things like maybe we have some treatment variable at the student level that we want to randomly vary, and we have, maybe some classroom level data that we want to randomly vary also at the school level. So maybe we have 3 or 4 or 5 different variables that are randomly varying at higher levels, and we just want to estimate the variances of all of those variables and not the covariances. If that were the case, we wouldn't have to do this dummy coding, but we would want to do this double bar still. Okay, so that double bar is going to estimate each variance of whatever variables are over here, but it's not going to estimate the covariances. Yes, Tui?
Sorry, can you say it again? Why we don't want to estimate the covariance?
Because this is just an alternative specification for the residual variance covariance matrix. So basically, if you're estimating the variance of the intercept, the variance of the slope, and then let's say you have some additional variables that are randomly varying too. So you have variance of treatment and variance of, say learning disabilities category, and the variance of something else. So you have like 6 different variables that are randomly varying across schools, right? Then estimating all of those variances and the covariances among all of them is going to be a lot, right? That's going to be a lot of things to estimate. So your model is going to be really complicated, and you might run into model convergence issues. So your model just might not really be able to fit because it can't fit that complicated. Essentially, it's like, the way I like to think of it is you have data and you have theory, and you can often think of reasons why specific variables might randomly vary across higher levels, right? So I think of things like, let's say, like race ethnicity variables. You can imagine why those might randomly vary across schools, right? Maybe some schools, you know, there are racist administrators, and so there's really big effects in those schools. And then in other schools, they have much more welcoming and, you know, whatever. And so then there's very much more small effects in those schools, right? So theoretically, you should be able to estimate that. That kind of makes sense that that would randomly vary. But if you try to estimate every single race ethnicity category that you have as randomly varying, then your model is going to be swamped, right? And so you're going to end up basically, you're trying to pull more information from your data than your data has to give, essentially, right? You're trying to estimate too much from your data. It doesn't have enough variance to give you good estimates for all of those things. So even though theoretically that might be the case, you have to simplify your model in some way to get it to actually fit. And so then you say, well, even though we could theoretically think of reasons that the effect of race ethnicity on achievement might vary across schools, there wasn't enough information in the data to estimate that with any sort of level of precision. That makes sense? Okay.
That's really helpful, Daniel. I was curious if, I don't know if you can say this definitively, but if for like smaller sample sizes or just areas like that where you have issues, would that be a case where you're going to want to take off some of that computational load? Or is that, I'm sure there are plenty of other variables, but sample size is for me what's coming to mind.
Yes, sample size is a huge, huge part of it. The other thing is, though, too, even with large samples, you might have really low base rates with things. And so specifically like things like interactions are really small. Like they're just almost always very small. And so like, again, you might have like a treatment variable, and then you have some moderation questions. So you're saying, you know, is treatment predicted by fidelity of implementation, right? So then you have some slope for treatment, and then you have some fidelity of implementation measure that you're saying, does the slope related to the treatment depend on the fidelity of implementation? And so that's a very clear reason, like area where you could say, yeah, okay, this is going to randomly vary across schools because fidelity of implementation is going to. And you could have fidelity randomly varying across schools, but modeling the interaction between fidelity and treatment as randomly varying across schools is probably not going to work, because it's just the variance is going to be so small that you might be able to estimate the variance if you did something like this, but you're almost certainly not going to be able to estimate the covariance between that interaction variability and other things that you have randomly varying. And so you'll see that with LME4, where you'll have the estimated variances, but then when you look at the correlations, they're going to be 1.0 or negative 1.0. And that's basically just saying, like, you can't estimate it. There's not enough information in the data. Okay, so here, when I do this with this double bar, right, you can see down here with my random effects now, I have a variance at time point 1, a variance at time point 2, a variance at time point 3, and a variance at time point 4. Okay, and so these are all different. Notice, though, they're not like dramatically different across them, right? And so that's actually pretty good evidence that you can simplify this by just fitting a single variance, and you're going to probably do just about as good. Okay. Also, I wanted to point out with the formula up here, it breaks out the formula like this. This is the exact same as this. Okay, so either way, it's the same thing, but that's another way that you can specify it. Okay, so as I mentioned, this double bar is going to make all of those random effects on the left side be independent. So you're not estimating the correlation across them. And if we pull the residual variance covariance matrix now from this model, you can see we get the estimated variances at each time point, but we just have dots here. And this is because it's a sparse matrix, so but these are not estimated. These are 0. Okay? Okay, so again, I've kind of already mentioned this, but how reasonable is it to assume that the variance of one time point, well, that sentence doesn't really make much sense. How reasonable is this assumption that we have different variances, but they don't have any relation between each other? Probably not very much in a longitudinal model in particular. But if we had a cross-sectional model, it might make some sense. Okay, and again, it could just be a way to simplify the model to get it to run. So that's what this is saying, right? Sometimes we can't reliably estimate all of those covariances, so we simplify our model by making stronger assumptions about the data, but it allows us to actually estimate the thing that we're interested in. Okay, so what we had fit before, I had referred to as an unstructured model. I mentioned that Singer and Willett refer to that as the standard multi-level model. That's what LME4 will do by default, but we can actually estimate a fully unstructured variance covariance matrix. So that's going to look like this. Okay, so we have time, and now this is all the same, but I just have a single bar like normal. Okay, and so that's going to estimate not only the variances in like separately at each time point, but now we're estimating all those correlations too. Okay, by default, LME4 will actually say, don't do this. This is a crazy complicated model, and it's saying the number of observations is equal to less than or equal to the number of random effects. Okay, so in this case we have exactly equal. That's just a model check that it does for you, where it's trying to prevent you from fitting overly complicated models that probably don't make a lot of sense. But in this case, I think you could actually make the argument that it does make sense. It's just a really, really complicated model. So as long as the number of random effects doesn't exceed the number of observations, we can do this. And in this case, they're equal. Okay, so you can just tell LME4, don't do that check. Okay, so you say control, Elmer control, check in obs first, and random effects equals ignore. This is one of those things I can never like remember what the code is to do that, and I don't do it very often. But so this is just like, look at the help documentation and you should be able to figure it out, or come back to these slides, which is probably what I'll do in the future. Okay, and then now we look at fully unstructured, and notice we have different variances at each time point that we're estimating, but we also have the correlations. Okay, and so this is different from that standard multi-level model because we're only actually estimating one variance for the intercept and one variance for the slope, and then we're sort of combining those to get that diagonal and off diagonal as being different numbers. In this case, we're actually estimating separately each variance and then combining those to get the correlations and things. But notice, see here we have these correlations of 0.9 and 0.94, 0.88, like those are pretty high. So we have some evidence here that we may be starting to overfit. They're not at 1.0 though, so that's good. Yep, Chris?
If we had like a model that didn't have significant variance and covariances amongst things, do you tend to just estimate it if it isn't giving you some sort of convergence warning, or to go through the process of like turning the model into something like this that doesn't have the structure because it was non-significant?
Yeah, so a couple of things. With LME4, you can't actually test the significance of the random effect. You would be doing some model comparisons where you're looking at things like AIC and BIC with one model that has it estimated and one that does not. So that's the first point. But the second is I would tend to lean on theory for that. So for example, if I'm estimating a growth model, I'm going to try to estimate a random intercept and a random slope because it makes theoretical sense that students would all have a different starting point and they would all progress at different rates, right? So because that theory makes sense, unless I'm running into model convergence issues, if I can estimate those things, even if the variance is small, I'm going to estimate them because it makes theoretical sense. The last point is so there's some people that will do things like they'll recommend that you check the ICC for an unconditional model. And if it's not very large, that you just go ahead and forget about multi-level modeling and move forward with just standard regression. I would argue that you should not do that. And the reason is because occasionally when you include additional predictors in your model, that can actually increase the ICC. So now you actually do have some dependencies between schools that you didn't have with the unconditional model or between whatever your units are. So as I sort of mentioned in the first class, I think it's best to have multi-level modeling as your default. If you're getting exactly the same results between both of them, between standard regression and multi-level modeling, then fine. But I would argue that it's better to have multi-level modeling as your default versus standard regression as your default. Does that help?
Yeah, thank you.
Yeah. Okay, so this is all, I've already talked about all of this, just the difference between unstructured and sort of fully unstructured, or what some people refer to as like the standard multi-level model and the unstructured variant. But just if you hear those terms, unstructured variance covariance matrix, you might want to pry a little bit more to figure out exactly what they're talking about. Because it could be that they're talking about the standard multi-level model, which is actually the terminology I would use. But it could be that they're talking about this much more complicated model where they're estimating everything, basically. Okay, so now, for the first time, we're going to move away from residual variance covariance matrices that we can fit with LME4, and we're instead going to use autoregressive structures. Okay, so there are lots of different types of autoregressive structures. If you took a class on time series data, you'd learn about a bunch of them. We're going to fit what's referred to as an AR1 structure, autoregressive 1 structure. Okay, so what is interesting about this is it includes one variance that is estimated as the diagonal, and then it has these band constants. Okay, so theoretically, let's say time point 1 and time point 2, those should be probably pretty highly correlated, right? Or at least they should be higher, they should have a higher correlation than time point 1 and time point 3, which should have a higher correlation than time point 1 and time point 4. Okay, and so that's what an autoregressive structure is. It's going to estimate essentially this like decay, right? So when time points are right next to each other, they're going to be estimated as being strongly related, and that relation is going to be the same for the band diagonal for all time point 1 and 2, time point 2 and 3, time point 3 and 4. Okay, and then a different diagonal is estimated for time point 1 and 3 and time point 2 and 4, and then a different one for time point 1 and 4. Okay, what's also interesting about this, though, is that we actually still only estimate one variance component, which is sigma. Okay, so we're not actually estimating intercept or slope variance here. Okay, what we do is we tell it the structure of the residual variance covariance matrix, and then we estimate sigma, and then we estimate this rho parameter. Okay, and what that is the amount of decay each time. Okay, and it's just a single parameter, just one parameter, and it works like this. So this is our variance, right? And it's going to be the same for the entire diagonal. Then we multiply that variance by rho. So rho goes from 0 to 1, right? So if this is like 0.8 or whatever, then this would be 80% of the variance at this time point. Okay, and then for the next band diagonal, we square that number, that rho. Okay, and then we cube it, and then we would raise to the 4th power if we had further, etc. Okay, so we're only estimating one variance here, sigma, and then this additional parameter rho, which I think actually NLME refers to as psi or something like that. Okay, so please do this with me. Let's go ahead and load NLME. And then we're going to now use the GLS function from NLME, which is different than what you will mostly see with NLME, which is we use LMER, right? Linear mixed effects regression. And in NLME, you can fit the same types of models generally using the LME function, linear mixed effects. Okay, so, but GLS is not estimating the variance components like we do with standard multi-level models. This is instead estimating an autoregressive structure. Okay, so this first part is just the same as like LM, right? We're going to say opposites naming data is predicted by time. The data is going to be Willett. And then this part is where we specify the residual variance covariance structure. All right. So we say correlation is equal to core AR1, autoregressive 1, right? And we say the form is equal to 1 by ID. So basically the intercept is going to randomly vary across IDs. Although that's not actually what we're estimating, but you can sort of think about it in those terms a little bit. Notice in this, when we're doing this too, we also have to use the tilde here. Okay, so this is actually a formula, but we don't have a left side hand of the formula. We're just saying this part. Okay, so this part is a little bit different for sure. The rest of this is pretty straightforward. Are there questions on this sort of syntax? So because we're saying by ID, we're saying we're going to estimate this autoregressive structure where the block diagonal is going to be specified by ID. Okay. So after you do that, you can call summary on your object. And as I mentioned, you don't have random effects here now, like you do in typical multi-level modeling. We have an intercept, we have a slope, and then we have this phi parameter, which is what I was calling rho. Okay. And down here you have the correlation and you have the residual as well. So you are estimating one variance component, which is the residual variance, right? But that's it. Okay. Now from here, we're going to pull out the composite residual. Okay. So if I have AR, which is what I called my model, you have from there this model struct thing, and then this core struct thing. Okay, this is going to give you, and then I'm saying give me the correlation matrix for this. Okay, that's going to give me all of them. So it's going to be a big list, an R list, where we have the correlation matrix for every single student. Okay, so that's why right here, I'm saying just give me the first one. So I'm using these double brackets to index the list. I'm saying give me the first element of the list, which is going to be the same for all of them anyway. Okay, it makes no difference. And then I say, so I call this CRAR. And what we see here is we have the residual variance covariance matrix. So this is the composite residual, but this is in terms of a correlation. So it's just going to be 1 here, and then 0.825. So this is phi, right? This is what we estimated. And then this is phi squared, and this is phi cubed. Okay, so we have these band diagonals. Okay, and what we can do is we can multiply this residual correlation matrix by sigma squared, which is going to be our residual variance, right? And now we get our composite residual in terms of variances and covariances. Okay, so you can see the variance at each time point is the same, right? And then we have this band diagonal structure. So this is, there's higher variance there and then lower, but we have, it's like the composite structure is theoretically based, right? So where we're saying these time points that are right next to each other are going to be strongly correlated. And then as we get further away, they're going to be less correlated. So we have this decay. So earlier, Lindsay, you were asking if I would report this stuff. If I fit this model, I would probably report phi. And I might even print the matrix like this as a table in the paper, right? Maybe not a variance covariance matrix, because I think correlations are more interpretable, but you could report what the variance was and then show this correlation matrix. That's probably what I would do. Okay.
Daniel?
Yep.
If you were using a sort of more minute time variable, like let's say you split the year into 365 days and you have like would you still use that autoregressive structure and just phi would be a very small value, but you would I guess that just seems like then you would be I mean ostensibly then you'd be estimating phi to the power of 365 at some point.
Yeah, which would be, you know, a tiny number. So that's that is sort of how it works, right? So you would be saying, like, let's say you had something where you were like looking at weekly data and you had like 52 weeks, right? So then you would have a strong correlation potentially between data points that were 1 week away, but not a strong correlation at all for ones that are 52 weeks away.
Mm-hmm.
So it is just more theoretically based, and you're estimating this single phi as, you know, in a way that will minimize the sum of residual squares, just like in standard regression. Okay, so we can see this if we want to. So this is what we estimated phi at, right? And so here's our sigma, that's our variance. And then this is the first band diagonal. So we're just multiplying our variance by that number. This is our second band diagonal. So we're multiplying by that number squared. And then our third band diagonal, multiplying by that number cubed. Okay. All right. Another structure that we can do is called heterogeneous autoregressive. And what we're doing here is it's going to be the same as an autoregressive structure, just like we had just a minute ago, except rather than estimating one variance across time points, we allow separate variances at each time point. Okay, so we still are only estimating one phi, so that decay is going to be the same, but the band diagonals will no longer be equivalent because of the different variances. Okay, so it's going to look like this: separate variances, right? And then here we're going to have this variance times that variance times phi. So because this variance is different from this one, this band diagonal is not going to be the same. Okay, it is still reducing at the same rate, but because of the different variances, it's going to basically look like an unstructured variance covariance matrix. Okay, this one is a little bit more complicated. And I'd like you to go ahead and fit this one as well. So the code here, I would use, this part is probably, you know, not horrible, but the next part where we pull the residual variance covariance matrix is pretty gnarly. Okay, so this is like reference code for you to come back to if you want to do this sort of thing. Okay, I wouldn't expect you to have it memorized. Okay, but what we're going to do is we're going to specify correlation just like we did before, core AR1, but we're also not going to specify these weights. So I'm using var ident, as in the variances of the identity matrix. So I don't know why it's called var ident exactly, because an identity matrix technically is all ones on the diagonal, but sometimes people say identity matrix to refer to the variances of a variance covariance matrix. But notice here for the form, instead of saying one ID, we're saying weights. So we're saying different weights for each time point. Okay, so the form for the AR1 is, you know, the intercept by ID, but here we're saying different weights by time. Okay. We can look at the summary, and it looks like this. Notice we have one phi again, which is here, right? But when we pull this thing, this is what I was talking about as sort of reference code. If you want to walk through this line by line, I think you can probably parse what's going on here. But basically, this is the correlation matrix. Well, this is a correlation matrix. We're multiplying that by sigma, and then we have the variances here. So we have these like coefficients, which are the weights for each of them. So if we go back here, we have these things, right? That's what's giving us the different variances. And so we end up with a variance covariance matrix that looks like this. So again, these variances are different. The rate of decay is the same, right, across each of these, but they look different because the variances are different. So this is still a simpler model than the fully unstructured model for sure. And it's just kind of a different model than the sort of standard multi-level model. Okay, but it's definitely more complicated than an AR1 autoregressive model. Yep, Chris?
I feel like I'm asking a million questions today, but
No
could
worries.
you give a theory explanation of what this model is saying? Like, let's say we were fitting this model. What are we saying about what the process that's happening?
Yeah, so I mean, basically, it's just if there's something that is happening within your study that is leading you to expect that the variability in the scores of students' tests are going to be different across the time points, right? And so there's reasons you could think of that, and your other model is constraining those to all be the same, right? Whatever the variance is at a time point, it's the same across all time points. And so here, like maybe part of the treatment is that you're kind of expecting scores to kind of converge over time for students who are high and low or whatever, right? And so that might be in a case where you want to say, okay, well, I can't assume that the variance at each time point is going to be the same. So I want to estimate separate variances like this, but it's going to be too complicated to estimate a fully unstructured variance covariance matrix. So I'm going to assume this like this same sort of decay that I had before.
And so all of the students will have identical across them, but the waves are sorry, the like wave from wave 1 to wave 2 for every student is going to be the same, but that's different than wave 2 to wave 3, correct?
Yeah, so the rate of decay is going to be the same. So just like before, you know, when you're estimating this variance, it's going to be like basically this and this times whatever that phi is. So this 0.817, right? And that 0.817 is going to be here, it's going to be here, and it's going to be here, right? But notice this number here is quite a bit bigger than these numbers because we have a big variance and at time point 3 and 4. So here you can see like we have really quite a bit smaller variance at time point 2 than we do at any other time point. Okay.
Okay.
So you're making fewer assumptions about your data, but it is a more complicated model now too. The last one that I wanted to talk about is this Toplet structure. And it is similar to the autoregressive in that we have a constant variance across the diagonal. But unlike the autoregressive, it does have band diagonals still, just like the autoregressive. But what's interesting is instead of estimating one phi, we estimate multiple phis. So each band diagonal gets its own phi estimate. Okay, so it's sort of a compromise between the previous two in some ways. Okay, so it looks like this. We have one variance, but then we have this variance here that's, or covariance, which is the same across all of them, but the decay from here to here is estimated. And then we have this band diagonal also, and the decay from here to here is also estimated. So it's not the same rate of decay across all of them. Okay. So instead of doing, you know, phi and then phi squared and then phi cubed, we're actually estimating different phis for each of them. Okay, so what we're going to do here is we're going to say GLS, and then this is quite a bit simpler than the heterogeneous autoregressive. It's much more like the autoregressive. We're going to use core ARMA, and then form is like that, just with ID, right? But we have this additional argument P, okay? And that's the number of fees that we're going to estimate. And we're going to estimate 3 of them because we have 4 time points, right? So we have the decay from here to here, the decay from here to here, and the decay from here to here. So we're estimating 3 sort of decay parameters. Does that make sense? Okay, so finally, we estimate the model, and it looks like this. So notice we have phi 1, phi 2, and phi 3. Okay. And so then if we want to extract the residual variance covariance matrix, it's just the same as the autoregressive. We first pull out the correlation matrix, and then we multiply that by sigma. Okay. And we end up with something that looks like this. So notice we have the same variance, and we have band diagonals, just like AR1. But in this case, right, this rate of decay is not assumed to be the same over time. So the change from this variance to this one is estimated, and then the decay from this one to this one is estimated, and the one from this one to this one is estimated. Okay, does that make sense?
I have a question, particularly like I noticed that we had one negative fee, and does it say something like the break of the continuity in the like how to say, like the growth trajectory or something like that?
Yeah, so you're thinking sort of like a discontinuous type of thing. Is that what you're saying?
Yeah, I think so. Yeah.
Yeah, I don't think so. I am not 100% sure, but I think you could probably walk through these calculations just like we did before, and you would end up with, you know, these numbers. And so it's just basically a way to estimate what that rate of decay is. I think it does go from -1 to +1. But yeah, actually, I mean, that kind of surprises me too. So maybe I need to look into that a little more. It seems like it would reverse the effect, sort of. Which is maybe what you're saying. Yep.
I'm having trouble understanding, like this makes sense conceptually for like most longitudinal models. I guess I'm having trouble understanding like when an like why the unstructured model is more theoretically justified than applying an autoaggressive variance structure, because it just seems like conceptually your variability or your like variance always is going to have this sort of decay with greater periods of time.
Yes, for sure. So it's really not about one being more justified than another. It's more about 2 things. A, sort of what you can actually estimate from your data. So this is this one, but particularly the AR1 model is going to be a significantly simpler model than this sort of standard multi-level model, right? And so in some cases, that's like going to be the best you can do with your estimation. And it is theoretically based, right? But it's also making stronger assumptions about your data than the unstructured model is, because the unstructured model isn't going to have any restriction on this sort of band diagonal. So these band diagonals make theoretical sense, right? But you are now making an assumption about that decay that you are not making with the standard multi-level model.
Okay.
Does that help?
Yeah. Like they might still have this sort of autoregressive pattern in the unstructured variance.
Yes.
Not constraining them to have it.
Yes, exactly. And most of the time they will. And so that's why this model can fit better sometimes, because if you are estimating all of these parameters and then you end up with a residual variance covariance matrix that very much looks like an AR1 structure, then you're going to have a much better fit to the data if you just estimate the AR1 model, because it's a much simpler model. You're estimating far fewer parameters and you're getting basically the same results.
Mm-hmm.
Could I follow up that question?
Mm-hmm.
Is there a way to, I mean, I imagine this would have to be like a package that would do this, but unless you were really good at matrix algebra, to like go into your variance covariance structure and to see what it is really similar to, like would the decay be this or that or whatever? Do you know what I'm asking?
Yeah, so I think so you estimate it with an unstructured model, and then you say, does this look like any of these other simpler structures, basically? Is that what you're saying? Yeah, so
Yeah.
I don't know of any way to do that. The only thing I would say is so sort of two things. If you're not running into any like model convergence issues, then yes, this might end up being simpler and a better fit to your data, but you also could probably just go forward with it and you're going to be fine. Where this really comes into play for me anyway is when I can't estimate the model without simplifying something. So that's sort of the main reason that I would use this. But the other thing is, I don't know of any way to look at like an unstructured variance covariance matrix and say, what does this most resemble? But you could just do what we're basically doing here, which is fit multiple models and then compare the fit of those different models. And then you can say, this one's simpler and it fits the data just as well. So therefore it's preferred because it's parsimony.
Cool, thanks.
Mm-hmm. Okay, so here we are comparing fit. Well, that's weird. I have some warning here that I was not expecting. Whatever, it works. So I'm using performance, and then we're saying compare performance across these different models. Yeah, Lindsay?
I don't know if this is like an easy, quick class question, but I am still having issues with compare performance. Like even when I look at the trace, it's just not working.
Yes, so I meant to send out an announcement about this. I think the CRAN version of the performance package is not working. So if you go here, oops, that's not going to work, is it? Let's say easy stats. Maybe that'll work. Yeah. This is it. So what you would need to do is install this directly from source. So this code right here, remotes install GitHub, easy stats performance. And then it should work if you're using the GitHub version.
All right, thank you.
Mm-hmm. Yeah, sorry, I meant to send out an announcement about that. Okay, so here I am comparing the performance of these though, and we can look at the AIC and BIC of these. And you can see I'm using GLS and LME4, and it's able to still, just pull out the AIC and BIC for those. And then this performance score over here is like basically model weights. So I showed you this within Sundry. I have an AIC weights function. This is the same thing, basically. I don't know if it's using AIC or BIC, but basically you're looking for lower values, right? And if something is more than 10 points different, that's pretty good evidence that that model is preferred. In this case, right, our best fitting model is the Toplets model, according to AIC, but it's pretty small compared to the autoregressive, or the just unstructured, the standard multi-level model. Okay, so we have 1277.98. So this is basically, these are separated by like 1 point. So the difference between those is not strong, but you do have a little bit of evidence that maybe the Toplets model is fitting better if you're using a AIC. According to BIC, it looks more like the AR1 structure. So in this case, you maybe get a little bit better fit by using these simplified models, but it ends up not being really probably too much of a difference. You can see that the variance component only model was horrible compared to the other ones. And the fully unstructured was also way too complicated, right? So it's fitting significantly worse than the rest of them. But all of these four are pretty darn comparable. So I think you could make a case for any of them. But as I mentioned before, the main reason I would go this direction if I were fitting models is if I was running into convergence issues. So I just couldn't get the thing to estimate. So I need to simplify it in some way to get it to estimate. Here we're comparing the actual coefficients from just the GLS models. You can see they're quite similar for these two. This one's a little bit different. And then these are pretty similar as well. AIC, BIC. So, and then we can look at the LME4 models. But why do we care about all of this? Really, as I mentioned, it's about model complexity, right? So if you have a very complicated model, then you might want to simplify it in some way doing something like this. Okay, I think that's the main thing to me, specifically if you're running into estimation issues. Okay, because again, there might be reasons why you want a lot of things to randomly vary across schools, but you just can't estimate all of those. So maybe you estimate just the variances of those and not the covariances or whatever. Okay, and if you have a time series data, then these AR1 type of structures are going to probably be pretty helpful as well. Okay, if you are estimating sort of like everything there is to estimate, then you're very likely to overfit the data. And so specifically, like with the fully unstructured data, we saw that, right? It estimated everything, but when we looked at the fit indices, it was quite a bit worse than the simpler models. So there's sort of two ways I like to think about overfitting. One is that the model has sort of learned too much from the data, or equivalently, we're fitting to the errors in the data instead of fitting to the sort of true population differences. Okay. And similarly, you can also think of it, as I said before, of like trying to pull too much information out of your data. So your data just doesn't have enough information. It's like squeezing water out of a rock, basically. So this is all stuff I've already said. As an aside, I think I've mentioned this already, but there is, this is the link to a document if you're having convergence issues with LME4. You probably will at some point if you haven't yet. As you build more and more complicated models, it ends up being difficult to fit everything that you think you want to fit, right? So that all fit function I mentioned is really helpful. The only problem with it is it's pretty computationally intensive. So if it takes, say, I don't know, say you have a really complicated model and it takes 10 minutes to fit, right? Then if you use all fit, it's going to take probably over an hour to fit, because it's going to fit the model over and over again with a bunch of different optimizers. But that still might be what you want to do. Okay, so that's a really good thing to do. And then if you're still running into issues, you can look here. There's some other suggestions there, but mostly it's usually going to be about simplifying your model in some way. Okay, so sort of wrapping up for today, and then we're going to move to homework 1 for the last like half hour. Okay, so as is probably pretty evident here, there are tons of different variance covariance matrices, like residual structures, that you could conceivably fit, right? With the combination of different correlation structures in NLME, and then those different weighting things that we saw too with var ident, right? However, essentially none of them are implemented through LME4. So all you can estimate through LME4 is the standard multi-level model, the fully unstructured model, or the variance component only model. Okay. Everything else, you're going to have to go to something different. So either NLME, as we did here, or you can use Bayes with BRMS. And even there, not everything is implemented, but a bunch of stuff is. Okay. Simplifying the residual variance covariance matrix can sometimes lead to better fitting models, and it might also help avoid convergence issues and overfitting. Okay, so those are sort of the main reasons that we would start to look at this. So that is basically it for today. And so next time we'll talk about modeling growth, part 1. Right now we're going to move to homework 2. So I'll go there in just a second and we'll walk through it. But before I do that, are there any last questions on the content from today? Okay. So let's go to homework 2. I mentioned this previously, but I will say it again. If you want to work in groups on the homework, that is more than okay. All right. Any of you can work together. You can even say, okay, obviously we both need to like read in the data, but you do number 2 and I'm going to do number 3, right? And as long as you sort of put your results together in a single document, that's fine, right? I will just give you the same feedback for both of you, and you'll both get the same score. As you probably saw in the feedback that I gave you, most of the feedback I'm giving you this term, because I am teaching another class and life is crazy, is fairly minimal, right? And it's mostly completion based, but not entirely. So if I see something that is wrong, I will dock points for it, but it's mostly completion based. And then the last thing is, if you submit your homework and you get something wrong and you lose points and you want to resubmit, I'm happy to take resubmissions if you fix your errors. Okay, so you can conceivably get 100% on every homework if you resubmit. Okay. All right. So for this homework, we're going to use a data set on adolescent alcohol collected by Curran et al. So this is just a link to the study, I think. And it has 3 waves of data on 82 adolescents. Okay. We have alk use, which is, waves of data were collected annually beginning at age 14. Okay. Alk use is the outcome, and it ranges from 0 to 7. And it was basically the sum of a couple of different items, but they have applied a square root transformation to it. Okay. And that's to get the data to look more like a normal distribution instead of like this skewed distribution. COA is a dummy variable indicating whether or not the participant was a child of an alcoholic. Okay. And then peer is a measure of alcohol use among their peer group. And just like alk use, it has a square root transformation that has been applied to it. Okay. The current data should be in Canvas. Current.
Yeah, Diego, real quick comment on that. Don't read in the current.csv. It's actually called alk-adolescence. I worked on the current data for 4 hours or so before I realized it wasn't the right data.
Wait, it's this data, not this data?
Yeah.
All right. Well, that is my mistake, so I apologize for that. I thought those were the same. But okay, so I guess read in this one, and I'll fix that. So I'll just rename this one or something. So I guess this one, alcohol adolescence, read in that one. It should have these variables. If you don't have these variables, then you're looking at the wrong data set. Okay. So we'll be, next time we're going to talk about modeling growth. And so there's some parts of this that are related more to that, right? Because this is due now 2 weeks from today. It's not due next week. So it's mostly the content from today's lecture, but there's some of it that's content for next week. Okay, so read in the data, conduct any data prep work you needed. And then this is the important part. Specifically, we'll be fitting a number of different growth models. So you'll need to think about how you're going to code time. Okay. All right. And then initial fits, fit a model with random intercepts and parallel slopes. Compare the fit of that to one with random intercepts and random slopes. Which model do you think fits the data better? Okay, so that's pretty straightforward. And then here, this is everything we did today, basically. This one and this one. So we're going to use GLS, okay, to estimate an autoregressive model, heterogeneous autoregressive model, and Toplet's model, okay? And then look at the composite residual from each of those. So specifically for all of these, you're probably going to just need to grab the code from the slides, but specifically for this one, which is a little more complicated, okay? And then you're going to compare the composite residual for those models to the composite residuals from these models. So when you're doing that, you can just use sundry to pull these, okay? But for this one, these ones, when you're pulling the composite residual, you'll need to probably use the code from the slides, okay? All right, Then compare the fit of all the models. Which model does the evidence suggest provides the best fit to the data, do you think? And then add some predictors. So include COA and peer as predictors in the model. Evaluate whether adolescent alcohol use trajectories depend on these variables. Okay, so this is, you want to look at that closely, right? We have these alcohol use trajectories for every student or every participant in the sample. And we're going to see if that slope depends on these variables. Okay, so right up here, right, I have you fitting models with LME4 and fitting models with GLS with an LME, and then you compare the models. Regardless of what you find is the best fitting model there, you can move forward with the LME4 models if you want. Okay, you can move forward with the GLS models also if you want, but you don't have to move forward with the best fitting model if you don't want to. Okay, this is sort of separate from the part ahead. Okay, so you're going to fit that model, which is a fairly complicated model. And so let me know if you have questions on that, but I think that should be clear. You want to see if the slope depends on these variables. And then provide a brief summary of your findings. And you don't have to interpret the entire model, just this part, right? Whether the trajectories depend on those variables. So you're going to fit that, and then you're going to make some conclusion about, yes, they do, or no, they don't, and here's why. Okay, here's why I thought that. And then finally, you're going to do a marginal plot. So again, don't worry about theming stuff, but basically you have 0 and 1 as, I should make that more clear. This is COA is what it is. And then this is peer group, okay? So, and then we got wave 0 to 2, okay? So you have different trajectories for COA and peer, or COA 0 and 1, and then peer as well. So different lines for peer and different facets for COA. All right, so that is the homework. It's due in 2 weeks. As you look at that, are there any questions that you have? Okay, so we have about 25 minutes left of class today. I will hang on here. If you want to get started on it and use this class time to start and then ask me any questions if you have them, you can do that. If you'd rather just log off and work on this on your own, you can do that as well. Okay, it's up to you. If you also want to use this time to try to talk to other people to find a working group, you can do that as well. And I'd be happy to put you in breakout groups if you would like that. So you can message each other or just unmute and whatever. Okay.